Morning everybody, and welcome to this guest lecture by Scott Fahlman on Cascade Correlation and Deep Learning. For those of you who don't, most of you should know Scott Fahlman at this point. For those of you who don't know, he's one of the original neural network Jedi Masters that in the world, and that CMU had. So he was actually instrumental in bringing Hinton to CMU back in the day. And Scott himself has a bunch of really seminal contributions to neural networks. Today, amongst others, you've learned about QuickProp. And in my opinion, his most interesting work was his work on determining optimal or greedy algorithms for determining the best network architectures. And that is the Cascade Correlation Framework. So Scott, over to you.
Thanks, Big Shaw. Everyone can hear me, right?
Yep.
At least you can. Okay, good. Well, good morning to all of you, or good wherever you are, evening, afternoon. It's always fun to give this lecture. I'll be talking about some work that's just about 30 years old. So, and now my screen won't, there we go. Be talking about some work that's just 30 years old, published in 1990 and 1991, on an algorithm I called Cascade Correlation, and a recurrent version of Cascade Correlation. And I worked on this for a few years, and then all the money for neural net research in the US went away for almost a decade. And so I went and did other things. I've come back to this a little bit. I'm primarily working on symbolic approaches to AI these days, since the whole rest of the world is doing deep learning. But I've been working with some students to look at these old algorithms again and see if they have some relevance to the larger problems that everyone's working on today. You might imagine 30 years ago, we didn't have computers with graphic processing chips of any kind. All the work I'll be describing was done on vintage 1990 computers, big old hulking things sitting on a desktop. Okay, so these are the two papers I'll be talking about. You can find them online under my homepage. And yeah, it was 28 years ago. The algorithms I'm describing are arguably the first deep learning networks. Why do I say that? They routinely built useful feature detectors that were 15 or 20 or 30 layers deep. And that's what all the excitement in deep learning is about. You can build, in deep networks, you can build complex feature detectors. As we will see, this builds some fairly complex ones. They build just as much network structure as they need during training. So you don't have to guess the network size, number of layers, number of units, and so on before training. We'll be talking more about that. These algorithms solve some problems that were considered very hard at the time by the neural network community. And it solved them 10 to often 100 times faster than standard backprop. So it was a big speed up. Ran on single core 1988 vintage workstation, which is what I had on my desk, no GPU. And of course, we never were able to attack the huge data sets that people do now. We didn't have giant libraries of photos to work on, or huge amounts of speech or text. That came along as the internet matured and people had access to much more data. So, what was I working on? I was working on two problems that I thought were pretty crucial to the advancement of neural networks beyond where we were in those days. And the first problem I was worried about is we had to, you've all seen this, even today, when you're given a problem to solve, a learning problem, and you're given a set of training data, which these days might be huge, there's still, you have to guess what kind of network size and shape, the learning rate, number and type of layers, number and type of units in each layer, the interconnection pattern. And there's really not much theory to guide us on that, even today. So people almost always go with whatever kind of worked last time for a similar problem and then mess around a bit. And this is one reason why deep learning as practiced today is still such a black art. People who've done hundreds of different problems and gotten decent results are in great demand because they've got a bunch of things. Oh, this looks like the problem I did a year ago, and this kind of network works, so that'll be my starting point. And then we'll mess around with it to see if we can improve the performance beyond what you get with this. So a lot of it is not theory, it's just kind of experience. So knowing what worked last time. A lot of hand waving, a lot of guessing. And even back in 1990, it was obvious that it would be really great if we could get rid of the guessing. So the first thing I did in this area was something called QuickProp, which I understand has been at least mentioned in the class. And it's just an algorithm that does simple backprop, but it learns the learning rate dynamically for the problem at hand. Instead of guessing that it should be 0.01 or whatever the units are that you're dealing with, it starts out with some initial units, takes a couple of steps, and then it notes for each weight the curvature of the space there. And it can fit a quadratic term through that and try to jump to the bottom of whatever basin you're sliding down into, or whatever peak you're climbing toward, depending how you like to look at these networks. So by just looking at the second derivative, you can get self-adjusting learning rates, and they can be different for every weight in the network. There still are parameters you have to put into QuickProp, but they're not the crucial ones. It's the learning rate is crucial, because if it's too high, you jump right past the answer. And if it's too low, you're creeping very laboriously down a slope. So that's QuickProp, and that did speed things up in the backprop world quite a bit. Often we saw a 10-fold improvement. But there are other things you have to guess, and the big one is the network size and topology. As I said, it's still a black art. Right now, there are a lot of people in the neural network world working on automated network architecture search, NAS. And the idea is to have genetic algorithms or any number of other things to try a bunch of different networks and train them up. And then if you're getting good progress on one of those, you look at similar networks, and it's all automated. But it's incredibly wasteful. It's hard enough to train one network on your data set. That's very time consuming. And to try 100 different networks to find the right one is 100 times more time consuming. And we're burning an awful lot of compute cycles because we don't have any guidance as to what kind of network we need for a given problem. And heating up the planet and building huge data centers and so on. So how can we avoid guessing the metaparameters? That's one thing that was very much on my mind, even after QuickProp helped with the learning rate. And the other problem is just, why is backprop so slow? Even with QuickProp giving you good learning rates, it seemed like it ought to be learning faster than it was. So I wrote a little visualizer, a little bit of software so I could see the networks as they learn. This ran on ancient operating systems, and I can't resurrect that viewer. But you could see what the hidden units were doing during learning, and you could look at them in different ways and see what part of the space they were clustering in, especially if you had a low-dimensional problem. If it was 2D, you could see them moving around. And once you could kind of see what was going on, it became obvious to me that there were a couple of problems. One is that the poor units are trying to learn to be useful feature detectors, but everything's a moving target. They're all being trained at once. So if you had only one unit that was learning, you'd be getting your inputs, you'd be seeing some residual error in the network, and you'd be trying to reduce that. You'd be adjusting your weights to get that done. And you can learn pretty fast in that case, especially if you've got something adjusting the learning rate for you. The problem is that all the other units are being trained at once. So the error signal you're working on suddenly is changing out from under you, and the other units are grabbing pieces of it, and all the units are interacting, and you're in this very chaotic space. So you can't go directly to the answer and nail it. You're you're cooperating with 1,000 other units. And they're all doing crazy things that you have no idea what they're doing. All you know is the error system is changing out from under you. And the other thing is a similar problem. It's what I call the herd effect. As you know, when you take a backpropagation network, you start it with random weights, chosen somehow, but basically random weights. And the idea is that each of these hidden units is at a different part of the space. So when an error signal comes along, one of them is closer than the others, and it'll kind of get there, and they won't all rush there at once. The problem is if you have a learning problem, and say you've got a single layer of 100 hidden units. That's what you need, that's what you have. You should be able to do the job, except each of those 100 units has to find a distinct job to do. There are 100 different jobs that you need to be done, 100 components of the error that need some kind of customized behavior for that component of the error. And the trouble is they're all seeing the same error at once. They're big components and small components. There's nothing centrally saying, okay, this hidden unit, you're going to go do that job. You're going to do this job. You're going to be looking for, we're trying to recognize the letter Q handwritten. You're going to be looking for the little thing that makes it a Q and not an O. Okay. And somebody else would do some different job. There's no central control over this. All the units are looking around at all the others, trying to find a job to do, trying to figure out what the others are doing. And after you watch this on a simulator, you see that they're running around as a herd. The initial variability, they're scattered all through the space of learning parameters. But when an error comes along, you're starting to train the thing. There's some big components that they all see, and they all go try to do that job. Oh, there's the big part of the error. I'm going to go over there. And so they all kind of converge toward the part of the space that will allow them to solve this part of the problem. Somebody gets there first, and then that component of the error goes away. You're solving that. Okay. But all the other units say, hey, I was coming over here to do a job, and now the job just disappeared. That error component is no longer around. Now what am I going to do? Oh, there's the second biggest component. I'm going to go over there. And the problem is that includes the unit that actually nailed the first part of the problem. So now it lets go of what it was doing, and they all go off. And then the first unit says, oh, wait, I got to go back. And no, but there's more to solve, and units get very confused. And eventually all the initial randomness washes out of the network, and they're running around in a pretty tight pack. You no longer have a lot of variability among the hidden units. So I call this the herd effect. It's like animals gathering into a herd for mutual protection, but they're not getting a lot of diverse jobs done. They're not finding smaller and smaller components of the error that are not solved yet and dealing with those. And the ones that are doing a useful job tend to wander off. So it's like this huge chaotic game of musical chairs, you know, the game where there's a limited number of chairs and a larger number of people, and when the music stops, you're supposed to get yourself into a chair. And it's just a mad scramble. So that's a very inefficient way to assign a distinct job to each unit. So these are both a result of all the units trying to learn at once. So it occurred to me that maybe we could solve both the hyperparameter problem and the slowness if we learned hidden units one at a time. Okay, let's start with a network with no hidden units and gradually introduce them, and then each unit can learn very efficiently. What's the biggest job? Over there, I'm going to go there, I'm going to do it. Now we nail him down, and then we put in, if we need to, a second unit. So that's the basic idea behind the Cascade Correlation Network. And here's a diagram showing, let's see, I made my cursor big so you can see it. Here's a diagram with inputs, adjustable weights, and outputs. So this is just basically a perceptron. Okay, there's some kind of activation function here as you do the output, maybe a sigmoid or something. And the idea is you put in the inputs, you've got the desired output, and you train these weights to do the best job possible of producing the outputs you want, of minimizing the error. Well, that's fine, but of course, as you all know by this point in the course, there are an awful lot of problems that you can't solve without at least some hidden units. Okay, this was the point of the book by Marvin Minsky and Seymour Papert, Perceptrons, that said without something like hidden units, you're just not going to be able to solve exclusive or any problem that looks like that. Without hidden units, each input is voting for or against one of the outputs. Okay, and it's not looking at what the other units are doing and hey, we could work together, so I'll get these and you get those. Okay, so we're going to need hidden units in the general case. We start out without any, we train it as well as it can, and now we're just looking at the residual error. We got the component of the error, the components of the error that can be solved without hidden units. So here we go, let's train up a hidden unit. I'll talk about how we do that in a minute. And this hidden unit now we can add to the network. It's trained up to correlate with some of the residual error, hence the name cascade correlation. And we train it up to match some of the error, and then we're going to add it to the network. So here's the first hidden unit. It's receiving all these inputs through trainable weights, producing an output, and that's now blended in with the raw inputs. And these output units can make a more complex discrimination. This is a little feature detector. Okay, we train it up, it reaches a plateau, it's doing as well as you can with one hidden unit. Maybe that's good enough. If so, declare victory and go home. Otherwise, there's some residual error that you still want to get rid of for problems like this. So what can we do? We can add another hidden unit. Train up another hidden unit to match some of the residual error. And if it matches it, we can blend this in and eliminate that component. And the second hidden unit not only looks at the raw inputs, but it looks at the output of the first hidden unit. Now, I've drawn these weights in blue right here because the idea is that once you add them to the network, you freeze them. This is a useful feature detector. We want to keep it. We don't want it to be cannibalized or pulled away to do something else. And when you add the second hidden unit, it doesn't bother the first hidden unit, but it does make use of its output. And then every time we add a new hidden unit, we train all of these weights in red to produce the best possible output with the initial features and with these new composite features. Okay, I hope that makes sense. One disadvantage of giving lectures over Zoom is I can't see if people are looking like they know what I'm talking about or they're totally puzzled. But I hope it's the former. To say a little more about the algorithm, you start with direct input-output connections only, no hidden units. You train the output layer weights using backpropagation or quick-prop, or it's just perceptron training. You're just training one layer of weights. There's no backpropagating through the network. There's nothing to backpropagate through at the start. And if the error is acceptable, quit. Okay, declare victory, go home. If not, there's some residual error you still want to get rid of. So now we're going to try to create one new hidden unit offline that we can add to the network. And then maybe a second one and maybe a third one, as we saw in that diagram. But right now we're trying to create the first hidden unit. I found that instead of just training one up to match the error, it's better to create a pool of candidate units. For reasons we don't fully understand, these units sometimes get stuck. They look like they're correlating well, but it's not really solving the problem. Some of them just get stuck in useless parts of the space. So we create a pool of candidate units. I was using a pool of about 8 of them. These days you'd use 8 million. And each candidate unit in the pool is looking at all the available inputs and all of the signals from hidden units that you've added to the network so far. That's their input. And then we want to train the incoming weights to these candidate units to maximize the match. I ended up using a covariance measure, not true correlation, but they behave pretty much the same. Between each unit's output and the residual error. Now, if you can correlate with the residual error, we can add you to the network and you can cancel some of it. Might be a positive or a negative correlation. Might be a positive or negative weight that you end up using. But if it's matching part of the residual error that you want to get rid of, you can now add it to the network, and it'll help cancel that. So you train the incoming weights to maximize the covariance between each unit's output and residual error. And you'll see that these are learning. Some of them get stuck. At some point, you say, okay, everything's kind of quiescent now in the candidate pool. We've been training away. And what we're going to do now is pick a winner, the one that's got the best correlation score, and add it to the active net. And as we add it, we freeze it, and we kill all the other candidates, and then we start over and train up some more hidden units if we need to. I call this tenure. We tenure the winning unit. It gets to be added to the net, and all the others get massacred. So that's like tenure in a university. The other thing about tenure is when you add this guy to the network, you freeze his inputs so that once he's got tenure, he's never going to learn anything more, never going to learn anything new. Okay, but the rest of the network has to listen to him now. He's now adding his detected features to the available inputs for the next unit and the unit after that. So it's very much like, metaphorically, like the tenure process in the university. You then retrain the output layer weights, find the new residual error over the training set, and repeat the cycle until done. Add a unit, add a unit, add a unit, train the output, see how the error is, add a unit, train the output, see how the error is. At some point, you either declare victory and go home, or it's perfect, or keep learning. There may be a limit on how many units you want to add, and that's fine. And to decide when to stop, we often use some kind of hold-out cross-validation. So you're learning on a training set, there's a held-out testing set, and you know that if you train too much on a limited training set, it'll plateau. And what it's learning from then on are just trivial details of the training set, not something that's going to generalize. So if you see the held out learning sets error go down, then you know you've kind of reached the point of no return with this data set, with this training data set. And it's not going to get any better. Okay, in terms of matching the larger universe of cases that you're going to actually run this network on. So you can use cross-validation to tell you when to stop. So here's a learning problem that we used back in the day. This was considered incredibly challenging. There are two inputs, two analog inputs, X and Y. And you're trying to teach it, you're giving it all these points. Black points want to give a 0 output, and white points want to give a 1 output. Okay, and you got a couple of 100 points. And you can see that this is not going to be learned by a perceptron. A perceptron can take the initial 2D space and cut a hyperplane through it. In this case, just a plane because it's 2D. But there's no plane that's going to help you separate the dark units from the light units. You're going to need hidden units for this. This is a classic kind of program where you need a bunch of hidden units, okay, to model the spiral structure of the inputs. You're trying to learn a manifold on which all the points lie, basically. And here's an output of one of the Cascor networks trained. It built 12 hidden units in this very simple space. And you can see that it's pretty much learned the spiral manifolds that are generating this. In fact, this was doing perfect on the training set. You can see that it's not generalizing perfectly. If there were a dot here, you'd want it to be white and it's black. Okay, so it's not perfectly smooth. There are various tricks that can be used to smooth this out, or you can have more data that forces you to model the space more precisely. But this basically is the output learned with 12 hidden units, the Cascor net. Now, how does that compare with what people had been doing? With the standard backpropagation net, 2 inputs, 3 layers of 5 hidden units. This was a pretty big network back in the day. It's laughable now. And 1 output. And you could present Oh, and this had not only total connectivity layer to layer, but it had shortcut connections. Nobody ever learned this task with standard backprop without using shortcut connections, meaning you're skipping over layers. Each layer is looking at inputs from all the previous layers and not just the immediately previous layer. So this is what people were trying to do, and they could actually learn this pretty well in 20,000 epochs. An epoch is a pass through the entire training set. Okay, so 20,000 passes through your training set with a couple of hundred training points. You could sort of learn this. So, okay, big network, and training it took 1.1 billion link crossings. In other words, this is a multiply add. Link crossing is multiply an input to the unit by a weight and add. This is how we measured actual runtime performance back in the day. I didn't want to compare my desktop computer's performance with somebody's supercomputer using clock on the wall. So the idea was to count the number of link crossings. If you're thinking of this in terms of doing dot products, the weights times the inputs, each link crossing is one multiply add step in doing those dot products. Okay, so that's a good measure, and you can translate that. It'll be faster, slower, depending on the machine, and if you had an ALU, it would be faster still. I mean a GPU. Okay, so 20,000 epochs of training on a standard backprop. Add quick prop, and it's sped up by a factor of a little more than a factor of 2. So this many presentations of the inputs. This is to get it perfect on the training set at least. Cascor took 1,700 epochs. So 19 million link crossings instead of 1.1 billion. Okay, so it's faster. It's a lot faster for this problem, and it learns it quite reliably. Sometimes it's builds 12 units, more typically 14, 15, 16. The smaller solutions tended to be smoother, so we favored those, plus it was faster to train. But this is the histogram of, over a bunch of trials, what size network this thing built in order to get that problem perfect on the training set. We found later that if you're more patient, if you burn more runtime on the thing, it gets down to 11 or even 10 as possible. But the network, as I described it with the parameters we were using, a reasonable amount of patience before you quit. The best answers had 12 hidden units. And they were a little bit shaggy, but they got the training set trained perfectly. Okay, so this was pretty exciting in the day. This paper got a lot of citations, and then there was this neural net dark age, and everybody forgot about this and went back to learning on fixed networks instead of something like this. One of the cool things is that you can actually see one by one what each new unit is doing with this particular problem, and you can see the effect it has on the output. So here's the initial problem. And without any hidden units, it ends up with the sigmoid saying definitely not, kind of maybe, and definitely yes. What it's doing is the only thing it can do is trimming off this row. Remember, it can just draw one line through the plane, basically, although in this case, it's a line with a gray area. And what it's doing is saying, well, there's a lot of white over here and a lot of black over here, and that's all we can learn. Okay. Now let's learn a hidden unit. So it, for some reason, decides to build a unit that cuts up through this way. And now the output, what it's done is learn to get some of these. There's a lot of white ones here and a lot of black ones here. So this is now trying to get that right. And if you look at the map of inputs to outputs, here's the 2D inputs, the output 1 versus 0. You can see now it's done something more interesting than just draw a line through the initial space. It's put a kink in it. You can build a kink because this unit is building on this unit. It's using not only the raw initial inputs, but the output of this guy. So now you can build a more complex filter. And then the next unit it adds looks like this. And it's building an even more complex filter. It's got a little hook in it. Well, that's pretty useful. Yes?
I have a question. Question on chat. What does the gray region in the picture represent?
The sigmoid is totally off, and then it's got a slope, and it's totally on. So this is saying the output is totally 0, something intermediate, and totally 1. Very close to 0, very close to 1, or some intermediate value. So this says we're in the slopey part of the sigmoid. Okay. If you use something like a ReLU, first of all, you can't use quick prop because it depends on second derivatives. But you'd have a sharp edge here of some kind. So here's the third unit added, and now look, it's building an even better hook, and now it's starting to build a spiral detector. And it's getting all these points in the dense area here, it's getting them all right. So it's doing better and better as it adds these units, and you can see that it's adding units that, when combined with the others, make a very useful feature detector. Ideally, you'd like a feature detector that just knows the shape of the manifold and says, yeah, okay, we're on it or we're not. In going from 7 to 12, now it's starting to grab. It's always symmetrical because it's a symmetrical problem and there's nothing to pull it away from that. But you can see it's starting to grab patches now. Okay, but it's doing better and better and better and better and better and better. And eventually you get to this approximation to what you really want. So I think it's cool to be able to see what each hidden unit is doing. Everybody worries about explainable nets, and this is not explainable like, okay, we see these 8 features and we know the patient should be treated in such a way. But you can at least see what it's trying to do. And you can even maybe predict what unit should come next, which is what the network's trying to do. So the advantages of this cascade correlation algorithm: no need to guess the size and topology of the network in advance. That was one of the major goals. It can build deep nets with higher order features. And back in the day, nobody was using networks with more than 2 hidden layers, maybe 3. Okay, they were just beginning to play around with convolutional layers. But this can build deep nets with higher order features that are handcrafted for the problem, basically. Well, automatically crafted. It's much faster than backprop or quick prop, anywhere from a few times as fast to 100 times as fast, depending on the problem. It trains just 1 layer of weights at a time, and that's very fast. You're not backpropagating through multiple layers of networks and getting this error signal that's all distorted by having come through that. You don't have vanishing gradient problems. You don't have stuck gradient problems, exploding gradient problems, because you're just training 1 layer of weights at a time. Okay, there's really no backpropagation going on in here. It works on smaller training sets, at least in many cases we tried. Old feature detectors, once added to the network, are frozen and not cannibalized later. So as we will see in a minute, this is good for incremental or curriculum training. You train it on a data set and it builds a bunch of things and it combines and it gets that data set right. Now let's give it a more complex data set. Instead of grabbing those old features and repurposing them, which messes up performance on the earlier data set, it leaves them alone, but it builds some additional structure on top of that and then tunes it all together. So this is very good for incremental curriculum training. And when we're training this pool of candidate units, they can all be on different machines. It's good for parallel implementation. They're not talking to each other. They're each looking at the training set, looking at the residual error for each case, and trying to tweak up their unit. And in the end, we say, okay, who's got the best score? Okay, but they don't have to talk to one another a lot during processing. So if you've got a bunch of separate ALUs or indeed separate machines, you can farm this out to multiple machines and then combine the results. Well, that's all very nice, but in those days, there's static problems where you want the output to be a function of the current input and nothing else. But we wanted to recognize sequences. We were hoping we could use this for speech, which came true, but with a different kind of network. We were hoping to be able to use this for stock market prediction, for anything with the time sequential component. And the problem is the network, as I described it, the output is just a function of the current input. It's got no memory at all anywhere. So what's the simplest possible extension we could add to Cascor to handle sequential inputs? Let's focus for now on a stream of discrete inputs, not the sort of time stuff you get when you're doing speech, which is all smeary. Speech can speed up and slow down, and it's still intelligible, so you need something that would be time elastic. This is for looking at a sequence of tokens, you know, polls taken every day, or a stock market price every day, or some speech that's been pre-processed to give you a string of phonemes rather than just a raw speech signal, which has to be massaged in the time domain. So what's the simplest thing we could do? Well, let's take the units we were doing before. Here's your hidden unit with the sigmoid output, but we're going to take the output, put it through a one-step delay, discrete time steps, and then feed it back to this same unit through a trainable weight. And these are trained just like Cascor units, then you add them and freeze them, okay? So this was just a very quick implementation that added this one hack. Every sigmoid unit you add has its own little memory of the previous state, and that's all. So this is the simplest possible way of dealing with time. So we tried it. I should say that if this self weight, looking at your previous input, is strongly positive, then you've got a memory cell for 1 bit. Okay, if this output is positive and this weight is positive, it's going to be saying stay positive. Okay, now it can be wrestled into submission by negative inputs on the other ones. But if that doesn't happen, it just stays positive forever. Okay, so it's got some memory of what it was doing, and it takes some inputs to pull it to do something else, to change its state. And if this is strongly negative, it flips over each time. We didn't see much of that. But if it produces a 1, it'll go through here. This is a 1, and the weight is negative. So now it's saying, okay, change your state, unless these units say stay there. These other inputs say stay there. So you can either create a flip-flop or a very simple 1-bit memory cell. So let's look at a sequential problem. And another problem people were working on back in the day is a very simple finite state grammar. Others had used this, so we had some benchmarks to compare against. And this thing is called the Reber grammar. So the finite state transition diagram, a B, and then with equal probability, either a T or a P. This is generating a string, okay, a grammar that generates strings. And the string will always start with B, begin, and then it'll produce either a T or a P, and then maybe some S's if it did a T, or maybe some T's if it did a P. So a typical legal string might be B, T, S, S, X, X, V, P, S, E. Okay, that's one of the strings this thing might generate. It can generate strings of variable lengths because it might or might not go around these loops. Okay, there's a big loop here too. So the idea is to build a network that, given the start of a string from the Reber grammar, will predict the next token in the string. We're going to train it up on a large set of strings and see if it can learn what the underlying pattern is so that it can predict. Having seen B, T, S, S, X, X, it knows it's either a V or a T there. So those two outputs are meant to light up and not the others. Okay, is that at all clear? Okay, so tokens are presented sequentially. We're trying to predict the next token. We're training the network to do that. The state of the art at the time was something called an Elman net. You had a single layer of hidden units. They would learn to produce the current output, and that whole set of things was also treated as an input to the network. So if you had a hidden layer with 5 units, those 5 values would be fed in as if they were inputs after the first time. And you've still got other inputs coming. So it was similar. It was this recurrent network. There was previous state being circulated and weighted and put back through the network. He was getting pretty good results. There's a fellow named Jeff Fahlman, who I believe is still working at UCSD, although I haven't crossed paths with him lately. Fixed topology with recurrent units. And you could use a 3 hidden unit Elman network, and it would learn this Reber grammar after seeing 60,000 distinct strings generated by the grammar, once each. Now, it did learn it in 60,000 distinct strings, but that was the best run they reported. They did not report how many times it didn't learn it, or how many presentations it took before they gave up or before they got some sort of success. So it learned this at least once, but we don't know what the average time it took to learn. The best time they saw was learning the Reber grammar perfectly after seeing 60,000 distinct strings. You could use a bigger network with 15 hidden units and then only had to show it 20,000 strings. Again, it got it right at least once, and might have been millions of tries, we don't know. They didn't report that. So recurrent cascade correlation, I made a fixed set of 128 training strings from that grammar. It learned the task building 2 or 3 hidden units. On the average, it took about 200 presentations of these 128 strings, or 25,000 string presentations in all. Okay, so similar number of string presentations, but I was working within a fixed set of strings. And every time it tested perfectly on new unseen strings. The network would learn it every time, building 2 or 3 hidden units. And when you gave it new strings from the grammar, it always worked perfectly. It's a very simple problem, so it's not like learning the grammar of English or something like that. But back in the day, it was impressive. And a much harder problem that people had begun to grapple with was the embedded Reber grammar. And the strings here start with a B, as before, and then it's either a T or a P. And then there's the string generated by this whole embedded grammar, which may contain P's and T's, by the way. And then when this grammar would exit, what it does is emit whatever token it saw before, and then the end token. Okay, so it's learning these complicated strings, but it has to remember this T value until the end. Okay, or if it was a P, it has to remember that toward the end. So there's one memory cell that needs to be set up, used all the way through all this confusion, and then harvested at the end. Or maybe the same functionality distributed over multiple units. Okay, so this is much, much harder. The Elman net, there were no reported successes on this task, even with 250,000 distinct strings and 15 hidden units. Okay, so a lot of cycles in those days was burned trying to learn this embedded Reber grammar task. With recurrent cascade correlation, we gave it a fixed set of 256 training strings presented repeatedly. Tested on 256 different strings, we ran it 20 times. Each run was overnight. Okay, you have no idea how much slower computers were then. And they had to be watched because they would crash in the middle of the night. You'd lose a day. Perfect performance on 11 of the 20 runs, typically building 5 to 7 hidden units. Okay. Now, ideally, it should have only had to add 1 more hidden unit, 1 more recurrent hidden unit. But, you know, the presentation of the strings was confusing enough that it added some additional structure. Okay, so not ideal, but it learned it every time to get perfect performance on the training set. And then when you looked at the test set, on 9 of the 20 runs, it was making some errors, but over the whole test set, only 20 errors in all. So it had learned it almost perfectly. And these guys never learned it. Training required an average of 288 epochs, 200,000 string presentations. Okay, so this was big, but it learned it perfectly most of the time, and learned a good approximation the rest of the time. So that was pretty exciting. A lot of people who'd been working on learning sequences went off and tried this on the stock market, and there were some additional problems there, partly because the stock market is subject to all these external influences. I wanted to have one more benchmark to put into the recurrent cascade correlation paper. So what we decided to do was teach it Morse code. Now, Morse code is dying away because everybody has phones that not only send speech, but also video and so on, and nobody is typing out. It used to be to get a ham radio license, an amateur radio license, you had to learn Morse code and pass a test on sending it, even though people were no longer using that. It was just a kind of nuisance requirement to keep the number of amateur radio operators within reasonable bounds. But this is a code that was used by the telegraph people, and they would use long or short. So the letter V, for example, is ... dash. Dot. And dash just had a longer period of time that it was held down. So this is an analog string, but we quantized it. And dot is represented by a sequence of inputs that's a 1 and then a 0. So a little blip and then it goes down. And a dash is 1, 1, a longer dip, and then it comes down. So we use this as our input encoding. And then when you got to the end of a letter, because there'd be 4 or up to 5 or 6 dots and dashes to represent a letter. When you get to the end of the letter and their variable length, it adds an extra 0 as a terminator. There's a little space between the letters. So letter V is ... dash, and it would be represented as this string, 10 dot, 10 dot, 10 dot, 110 dash, and that's the end of the letter, so you see a second 0 in a row. Okay, the letters are between 3 and 12 time steps. Okay, the simplest one is 100, that's 1 dot, and that's the letter E. Now, interesting thing about Morse, when he was inventing this for telegraphers, nobody knew about information theory in those days, but he did think it would be smart to use a shorter encoding for the most common letters in English.
Scott, I have a question here.
Yes.
How would you guarantee that the newly added neurons are learning the right direction? How would you distinguish between useful progress and useless ones?
When you're training the units in the pool, they are being trained to correlate with the residual error. And if they can do that, it's almost always the case that you can add them to the network, and with their additional input, it does better. Okay. Now, occasionally you will see a useless error created, and I've got a student looking into why that would be. There's something that correlates well with the residual error, but still when you add it, the network doesn't do that well. So my student, Dean Alderucci, is looking at that. But you just see if indeed you keep reducing the residual error, however you want to measure it, whatever evaluation function you're using. And if it does that, then you're moving in the right direction. None of this is guaranteed. It's greedy learning, okay? I'm certainly not making a claim of optimality, but I am making a claim that this muddles through better and faster than the existing techniques, which can get stuck. Backpropagation networks quite often get stuck, and you have to try again. So I hope that answers the question. So we're giving it these Morse code sequences. At the start of each letter, we zero the memory states, so there's no carryover from one letter to the other. After you see this 0, 0, it generates a signal that says start over. And what we want is the outputs are all 0 while a letter is coming in, and then at the end of the letter, it produces a 1 on the strobe, which says this is the end of the letter, reset the weights. And we want the correct letter to be high. Okay, so there are 26 outputs, and the letter V is one of them. And if what you see is this string, you want the letter V at the end to come up. Okay, the output for the letter V. So that's a pretty hard problem. We trained on the entire set of 26 patterns repeatedly. In 10 trials, we learned the task perfectly every time. it built an average of 10.5 hidden units, anywhere from, I think, 8 to 16 or something, but basically clustered around 10.5 hidden units. And the cool thing is it doesn't need a separate unit for every pattern. There are 26 patterns and only 10 hidden units. So there's some sharing going on, some cooperation going on. And it doesn't need a unit for every time slice in the strings. Okay, these strings are, the longer ones are longer than 10 time cycles. It learned these on an average of 1,321 passes through the entire 26 patterns. So that's pretty fast. That was surprisingly good result to me. And well, surprisingly good result. And it occurred to me that we might try curriculum learning on this problem. So instead of learning the whole set at once, we present a series of lessons with the simplest cases first. So E and T are the shortest ones. E is 1, 0, T is 1, 1, 0 with the extra 0 at the end. So this is 3, this is 4. We trained it up to learn these, just one or the other. And then when it was doing that perfectly, we increased the sequence length. We trained on these letters, which are a little longer, and these ones, which are longer still, and then this set of letters, which is longer still. And these are very long sequences because they're relatively rare letters. And we're just training first on this set, then on this set, then on this set. We're not repeating the earlier lessons at this point. Okay, it's getting each set right independently. It's building new structure as it's needed, but it's not going back. And finally trained it on the entire training set just to smooth out the result, to blend everything together. We ran 10 trials. E and T were learned perfectly, usually creating 2 hidden units, each addition, which is 2 bits of memory, by the way. Each additional lesson adds 1 or 2 units. And the final combination training to blend it all together added 2 or 3 more hidden units. Over 10 trials, all 10 were perfect, average of 9.6 units created. It required 1,427 epochs passes through the entire training set, or the subset of training, the small training set that you're teaching at any given time, versus 1,321 passes through the total training set if you're learning it all at once. So this is learning, these are much smaller epochs because it's only learning 3 or 4 or 5 new characters. Okay, so it's learning those. So some of these were to learn the ET, and then some were to learn that next longer set, and so on and so on. So it's the same number of total epochs, but these epochs here with the curriculum learning are much smaller. So on the average, it saved about 50% of the training time to break it up into a lesson plan, a series, a curriculum, a series of shorter lessons, and then building to the more complex ones, just as, well, metaphorically, just as humans learn.
So, Scott?
Yes.
As you go from the easy lessons to the tougher lessons here, does the number of neurons you require to make up for the difference keep increasing? I mean,
generally not, because it's got a lot of structure already from the previous training. So it's just adding 2 or 3 hidden units for each new batch. Okay. So, we looked at, but didn't get very far in implementing because the funding all went away.
Yeah, there's a question. So
yes.
why doesn't the network forget how to identify E and T if it hasn't seen them in training for a while?
That's why we need that training phase at the end. It built the right features for detecting them, but they have to be blended with all the other features at the end to make it smooth and get it right over the whole training set. So that's why at the end we train on the whole problem, including the old ones. Remember the E's and T's, you got to get those right too. And we go back and look at everything all at once. But that last bit of training is quite quick once all the features are in place.
Got it.
So there was something called Cascade 2, which used a different correlation measure. It seemed to work better for continuous outputs. I won't go into the details. A cool thing that we played with a little bit, but not very much back in the day, is using mixed unit types in the pool. So you can have Gaussian units, you can have edge detection units. You tenure whatever unit grabs the most error. So you got some sigmoids, some Gaussians. Whatever's getting the job done in the pool, he's going to have the best score, and you put him in the network. Okay.
So,
and you might end up with a network with some Gaussians and edge detectors and spiral detectors and so on. Yeah.
Question. As I keep increasing the size of the pool, doesn't the cost of evaluating the pool increase kind of rapidly? If I have one, it's just
the candidate pool's a fixed set.
Okay.
Yes, they have more and more inputs, so it increases a little bit the time required to train on the, and it's looking perhaps at more subtle and complicated error at that point because you've taken away some.
But you also have the problem of selecting the right entries from the pool to retain, and that's
but that's easy. They're all. So when you're training the candidate units in the pool, what we do is we run the network so far, and you've got all the different inputs. And for each of them, you're seeing whether the outputs of those feature detectors. We save that, and then we use that whole thing as the inputs and the residual error to train the candidate units. So we're not going through the old network at all. It's fixed. So we just look at the inputs and outputs for the training set. And that's what we use to train the candidate pool.
Yeah, but then suppose I have like, say 100 candidates in my pool. Will I be?
Okay, we never went that high, but okay.
But anyways, I'm just random number, right? Would I be retaining just one, or would I be retaining some subset because the cost?
All right, well, that's the point I was heading for here.
Okay.
Suppose you've got 3 or 4 units in the pool that are doing really well. Why not keep them all? Well, they might be totally redundant. They might all have learned the same job. So it would be useless to add 4 units when they're all doing the same job. But if they decorrelate one to another, then it's worth adding them. Okay, so that's a tweak we could add to this. If there are multiple high-scoring units that don't correlate with one another, they're finding different things, then sure, add them all. Now, we had not pushed in that direction or written any papers on it. It's I'm sure it will work, but you know, how much advantage you gain that way, I don't know.
So but that would be another loop of greedy selection within the pool.
Absolutely. Once in a while, you give a tenure to 2 faculty members on the same year. But only if they're different. If they're redundant with one another, you may as well fire one. All right. So different correlation measures work better. I talked about that. It bothered people that these networks were getting deeper and deeper, and you might not need that. Okay, there's kind of a propagation delay. So with a student, Shumit Baluja, I did write a paper about mixing descendant and sibling units. Got rejected. We kept working on it, but then we had to go do different things because there was no funding for this. But what you could do is have in the candidate pool some descendant units, meaning they make the network deeper. They look at all the previous units, and some sibling units that don't look at the last one, at the most recently created hidden unit. And if that works just as well, sure, add him. It's not making the network any deeper. You could even have some that are looking at previous things, just the raw inputs. Maybe at some point you want to have something that's just a function of that. So you could have units that are trying to make the network deeper and make use of all the existing structure and build on it, and other units that are taking another look at the inputs or just the input in the first couple of hidden units, and they're not deepening the network. It depends on the implementation when you want to actually deploy this on your iPhone. There may be an advantage in having the network not be too deep because it just introduces delay. But, you know, going through 6 layers of hidden units is so fast these days that nobody cares. So let's see. So we just talked about adding multiple new units at once. There was a fellow I was collaborating with at McGill in Montreal, Tom Schultz, whose group started using whole trained networks as potential new candidate units in the hidden pool. So these are features that you could add, and it's a whole trained network instead of some simple little thing. And you can train it just the same way. You can tweak it up, and you can add it to the network as a feature detector. It's a whole trained network in its own right, but you can add that as a feature detector along with some of the more simple units. So there are a lot of different things you can do moving in this direction. So key ideas. Build just the structure you need. Don't carve the filters out of a huge deep block of weights, most of which will be wasted. If you, there's been a lot of work now where you train a huge deep learning network and then you try to ablate away the stuff that's not doing any useful work and then have to retrain a bit. It's certainly more efficient if you can just build up from zero instead of taking a really huge network, training it, and then trying to carve bits away for deployment after it's trained. So build just the structure you need during training. Key ideas: train and add one unit feature detector at a time. Then you add it and freeze it. It eliminates the inefficiency due to moving targets and the herd effect. While you're training these candidate units, nothing else is moving. They're not looking at each other. The network is fixed. So nothing's moving. They can go right to the answer and nail a piece of it. And there's no herd effect. There's no moving targets. You're training one thing at a time. And when you freeze it, that's very good for the lesson plan training. You won't have what they call catastrophic forgetting now. You have a network that's doing one job, you train it on some new stuff, and oops, I forgot the first job completely. You've still got those hard-earned features that you built, complex composite features, and they're not going away. It's just how they blend into the output now, given the new stuff that changes. And the unit training and selection is very parallelizable. If you have a highly parallel machine or even a machine that directly implements these units, possibly made out of biological stuff that lives in someone's head, it's very parallelizable. There's still a lot of floating point math to train things, but it's still doing dot products, but you can train each of the units in the pool separately. And the key idea is to train each new unit to cancel some of the residual error, to correlate with it, and then you can cancel it out. And that's really the same idea as boosting, which came along a little bit later. So I invented boosting, but I didn't prove all the theorems and stuff, so I don't get credit for that. But this was a form of boosting. Boosting keeps looking at the residual error and adding imperfect new filters to the network, reducing the residual error. And others came up with some nice theorems that will get you to the goal eventually, with all sorts of caveats, of course, to make the theorems work. So I never went down that math route, but it was boosting. I still have the old code in Common Lisp and C. It's serial. It would need to be ported to work on GPUs, and we're working on that. I'm devoting a little bit of my time to this. I'm mostly working on SCONE, which is my symbolic knowledge representation stuff. It's not neural nets at all these days. But I'm interested in collaborating with people who want to take the old Cascor ideas and push them forward if they want to. I've got limited time I can put into that, but I'm certainly interested in collaborating and helping. Obviously, it would be really fun to try this on real natural language grammars and the kinds of, recognizing cats on the internet, all the kinds of problems that are so important now in the deep learning community. And adapting it to these much huger problems does introduce some issues, like how do you deal with, my student Dean Alderucci tried building a version of Word2Vec language model on this thing. And the biggest problem was that you've got this huge space of inputs and outputs. It's one hot encoding of thousands and thousands of words. And it was a little hard to fit that into Cascor. We're still struggling with that. Perhaps tweaking the memory delay model of recurrent cascade correlation would allow it to work on time continuous signals such as speech. if we knew anyone who liked working on deep learning applied to speech. Speech is time sloppy in a way that these discrete token strings are not, of course. I think it's fairly straightforward to come up with a convolutional version. Just some of the units in the candidate pool would be convolutional units that look at the whole network, slid around. And since you can train them in parallel, you can afford to have some of those. Each one's got a processor all its own, perhaps. And the hope is that this approach might require much less data and much less computation than current deep learning approaches. I think there's some things here that we might exploit and make some real progress on doing deep learning without heating up the planet so much. I've got one PhD student, Dean Alderucci, working with me. He's ported recurrent cascade correlation to Python. He's got some code he shared with others. I don't know how eager he is to just make it available to everyone. He's looking at using this kind of approach for natural language processing applications, specifically aimed at the strange kind of mangled English that you find in patents. He has in a previous life, he was a patent attorney, and a damn good one. And he's trying to use natural language processing techniques to figure out patents. And he's looking at recurrent cascade correlation as part of that portfolio. It's surprisingly hard if we want to resurrect this, and if it gets comparable results to some of the deep learning approaches others are using with fixed networks, with guessed networks that they had to guess in advance. The most likely thing we are is to improve the speed, the learning speed. And it's frustrating for us that the reported benchmarks out there, all the Kaggle problems and things that people are reporting, they seldom talk about the actual time required to learn the thing at all. And if they do, they tend not to, they might say, okay, we ran it on this huge room full of computers and it took 38 seconds or it took 38 days. But how does that compare to the computer that I might have access to, which might be different, might be very different in a lot of ways. So people are not comparing learning speed results very much, and it's hard to find benchmarks that we can say, hey, we did this in a tenth the time. Now, I think we can use something like this link crossing measure to compare the time required on very different machines. Almost all the time in all these architectures goes into dot products, basically. So if we know the number of multiply add steps in all those dot products, that's a very good surrogate for the total time required. And then you on your supercomputer and I on my iPhone can somehow compare our results, because we can both say, well, we did this many link crossings. If I can solve the problem at all on my iPhone. So I wish people would, and even if they report the speed to train the final network, they don't tell you how much time was wasted on other networks to find the right one. Okay, that's very seldom reported. So I'd like the community to pay more attention to total start to finish time required, including all the models they tried that and then quietly threw away and didn't tell anyone about. There's a workshop coming up at AAAI 2021 in February. It'll be a virtual workshop, of course, because we can't all get together, on learning network architecture during training. Biksha is one of the organizers, me, Dean Alderucci. We've got some other good colleagues who are helping to put this together. So this is just taking shape right now. We're about to start collecting contributed papers for the workshop and so on. So that's something to keep an eye on. Even if you don't want to be a participant, I think people will be able to join this as spectators. We're not quite sure how AAAI is going to organize that yet. So that's what I have to say, and I'm happy to take questions now. I can undo the screen sharing.
Okay, I have a question here, which is, how would this idea of cascade correlation apply to or relate to the field of explainable AI? After all, we're adding things one thing at a time. We're always correlating it to error. So does this somehow mesh with the notion of explainable AI? Or
yes, and Yes and no. The cool thing is you can see what each new unit that you add is doing. And you can, just as a network with a bottleneck is more explainable than one with just total connectivity. If you're going through a bottleneck, things that look like features may emerge. This unit here is on for all the female pictures, or all the pictures of black versus white people. And this unit here is long hair versus short hair. In the same way as going through a bottleneck makes a network more explainable, creating these hidden units one at a time, you can sort of see in many cases what each one is doing. I illustrated that during the talk. Now that's different than explainable in the sense of producing a coherent English description and being, you know, if you want to explain to the patient why you have to cut their leg off, you know, you can say, you know, here are the features we see in the x-ray, there's this and this and this, and we found that, you know, this is cancerous and it's going to take the following course of action if we don't do this. This doesn't give you that for free, but it does give you some raw material that might feed into that. I think for truly explainable AI, we're going to need a strong symbolic component, which is why I'm currently working mostly on that. Rules expressed in something more human recognizable than a pile of weights. But at least these weights are a little more coherent. They give you something to talk about because they tend to be not totally distributed representations that are smeared over hundreds of units. You often see a unit being created that's just getting the third dot in Morse code. Okay, and you can build instruments to tell you kind of what it's doing. You can build ways of displaying that.
So potentially one could think of the cascade correlation structure as some way of building structures that could be used in explainable AI because they are, after all, catching incremental errors, right?
Yeah. So Jeff Hinton did a really nice experiment back in the day with families. You had two big families with 3 generations of grandparent, parent, and kids. And there was one English family and one Italian family. Well, they had English names and Italian names. And these were all unary inputs to the network. And then there was another set of inputs, which are family relations. And so you would say, you know, Biksha, brother, some other value would light up. And that's the thing you were trying to train. Now, if you just gave it a standard neural network with dense interconnections, it would learn it fast. It'd be able to learn all the triplets that you trained it on, okay, and produce the right output given the relation and the subject, and it would produce the object. It would learn it fast. If you put it through a very tight 3 or 4 unit bottleneck, you would see that it was developing 1 unit for English versus Italian, 1 unit for male versus female, 1 unit for 3-state unit with grandparent, parent, and children's generation. The tighter the bottleneck, the more it had to come up with something that looked like symbols with a very unary representation where each dimension of the categorization had its own unit. It took much longer to learn. Okay, but if you have total connectivity, it just smears all the features over everything and it learns it very fast, but there's no way to tell what's going on. So this is a little bit like always having a bottleneck. The next unit is dealing with the bottleneck.
So there's a second part to that question. So can we think of this in terms of transferring whatever information the Cascor units have got into a different network? So could this be some kind of provide the basis for some transfer learning?
For the same reason it's good for curriculum learning, it would be good for transfer learning. It built this set of features, we can move that to the other network. It's got its own set of features, then we blend them and add some more features that combine them. So you can just take these hidden units that were learned, they're useful feature detectors, and you can take that whole subtree and move it. Or build on it and then clean up the mess later.
Very nice. So any other questions, guys? And
can we ask his voice?
Yeah.
Yes, hi.
Hi, I'm relatively new to deep learning. This is like my first course in it, and so I might have just misunderstood, but I was curious how you handle when the final output of the entire network needs to be in a different form. So the initial, say you know, an example is we're learning about CNNs right now. So you have a convolutional layer at the top, and at
Yes.
the end it needs to be looking completely different. And so you want to learn those initial parameters and then add new hidden units as you go, right? But then you would have another layer at the bottom that needs to transfer that into a form that you can use for your loss.
So you're changing the problem by changing the desired output format.
Yes.
Okay. Pretty much just what I was saying before. You train on output format A, and it builds a bunch of useful feature detectors. And now you say, well, I want the same input, I want the same outputs basically, but you have to represent it in a different way. You have to light up 2 letters at once or something. You can take the features that you've built so far, they're very likely to turn out to be useful because it's really the same problem, but with different outputs. You put in the new outputs, train it on that, but you keep that structure is fixed that you learned. And you might have to, you know, to meet the demands of the new output, you might have to add some more hidden units and layers. But mostly it'll be training the output weights to produce the new outputs.
Okay, thank you.
Any other questions, folks? So apparently not. So thank you very much, Scott, again. So we have a very enjoyable lecture as always.
Well, thank you.
And guys, again, to reiterate what I put in the chat, this is the incredibly open and yet promising area of research, because as far as from everything that we know, Cascor structures will give you somewhat minimal structures, which means you could get something that's maybe 2 or even 3 orders of magnitude smaller than the largest than current networks to achieve the same job, achieve the same performance. Which the cost, of course, comes at the cost is the cost of building up the network, simply because it's an incremental build-up process, and we have so many tools of parallelization that allows current systems to be pushed onto a GPU. So if you were working on a CPU, Cascor is the way to go. It's not very clear how we can do this on GPUs, but that's again a very open area of research. But if we could get it done, I think this is actually going to make a tremendous difference to the manner in which we architect networks.
And
So,
it's a relatively, sorry to interrupt, it's a relatively small sub area right now. This has been almost, I got a lot of citations for this. I don't know what the current count is, but then it was almost completely forgotten when the deep learning revolution arrived. So this is slightly virgin territory. It won't stay virgin for long, I don't think.
no, so again, if any of you are interested, I highly recommend that you pick it up because there's a lot to be done. Yeah. Right. Thanks again, Scott. I'm
Okay.
stopping the recording.
Thank you, and good luck to all of you in the rest of this course.